Welcome back to 8701. So again, we have now all tools in place to do a next round of cross-section calculations. We have seen how to set up a matrix element. We have seen how to build spin averaged or to treat the spin and then specifically to calculate spin averaged amplitudes using Casimir's trick. All right, I'm not saying that this is all easy now, but you have seen all necessarily elements to calculate a cross-section for a QED process. So let's summarize. So we have seen that we can set up the matrix element using Feynman rules for QED. We have seen how to set up the spin averaged matrix element squared using the traces. Now we would have to evaluate the traces in order to derive this formula here. So I spare you a precise discussion of this step here, but you can actually follow this quite straightforwardly. Let me just step back a little bit before we proceed. My goal for the class is not to have you calculate all kinds of cross-section processes, but to understand how you would do it for the purpose of really understanding where dependencies come from and where this kind of calculation has its limitations. The first part is you want to see, what are the dependencies on the number on the couplings involved. You see this G square, for example. That's a rather important effect. You also want to see, through Fermi's golden rule, how we get actually into the cross section from the matrix element calculation. So if you ever had to calculate a matrix element, and I'm going to ask you to do this once, maybe twice as part of the homework set, I encourage you to open a book, follow the rules, look up tricks, how to work with traces, and then you should get to a reasonable solution in a reasonable amount of time. But here, for the purpose of this discussion, we want to just have a look at a few specific cases where we make assumptions and simplifications to the discussion. So the first one is called mod scattering. So here, again, we are at this example of a spin half particle scattering with a spin half particle, a different spin half particle, through the exchange of a photon. So we used the example of an electron-muon scattering, but this muon here could also be a proton or any other nuclei with spin half. The assumption for mod scattering we're using is that the mass of this particle, the muon, is much heavier than the mass of the electron. And this is true that the muon is 200 times heavier than an electron. A proton is even heavier. Any heavier nuclei, obviously, is even heavier than this. In mod scattering, we also make the assumption that the momenta involved are lower than the mass of the heavy particle, and that the recoil of the heavy nuclei or the muon can be neglected. If we do that, we can then write the differential cross-section using Fermi's golden rule as a spin average matrix element squared divided by 2 pi m squared. Okay. If you then use this kinematic information, right, you basically start from this matrix element here, and then you use those vectors, those 4 vectors for your momentum of the first, second, third, and fourth particle. You find that many of the factors are simplifying to ME, so P2 times P3 is ME, and so are many of the others. And there's a few important factors. For example, P1 minus P3 square is minus 4P square sine square theta half. And similarly, P1 times P3. So you put this all in, again, starting from this very formula we just had discussed before. And you put all the simplifications in, you get this matrix element, which already, that looks much more manageable, right? There's an m square, there's a p square, there's a cosine square, theta half term, and some factor which depends on the momenta and the masses, okay? And if you then add this to Fermi's golden rule, you find this equation for your mod scattering. Again, this is the scattering of 2 different spin half particles, where one is much heavier, the outgoing momenta are small, and the recoil of the heavier particles can be neglected. So this MODS formula describes, for example, the Coulomb scattering, so the scattering with a photon on the electric charge of a nuclei. And the scattering particle is not too heavy and not too energetic, like an electron. We also assume that everything involved here is point-like. We haven't had any discussion on the charge distribution of the nuclei or anything. We're assuming that this is a point-like particle. Okay, we can further discuss now the case where the initial state particles are non-relativistic. So here our momentum formulas simplify. This is simply m squared, p squared is 2me, and alpha is q1 times q2. Those are the electric charges. And so then our differential cross-section further simplifies to something you have already seen. The differential cross-section is equal to q1 times q2 divided by 4 times the energy sine square theta half squared. And we have seen that as already the Rutherford scattering cross-section when we discussed cross-section measurements in a geometrical kind of sense. So this kind of closes the loop here in our cross-section discussion and how we can think about those things. The Rutherford cross-section is nothing else but a big billiard ball being hit by a small billiard ball, and looking at how the cross-section actually, how the cross-section differentially kind of evolves out of this setup. All right. In this sequence, we have a little bit more of a discussion. What happens now if we introduce higher order terms, and how can we think about those solutions? And then I have 2 extra lectures where we go back and discuss spin, and also how we can actually understand this in a Lagrangian setup.